Now let's solve for the voltage wave using the phasor version of the transmission line equations. We begin by writing I of x using the first equation, then substituting it into the second equation and rearranging to obtain a new equation. Next, we move negative omega squared times LCV of x to the left side, resulting in a differential equation. Since the coefficient omega squared times LC may look complicated, we can use a new coefficient beta squared to represent it. This form of differential equation is known as the Laplace equation, which may be familiar to those who have studied electromagnetism. Now, our goal is to find v of x from the second-order differential equation, whose characteristic equation is s squared plus beta squared equals 0. We know that the roots are positive and negative j beta, meaning the general solution of the voltage wave can be expressed as a times exponential 2 negative j beta x plus b times exponential 2 j beta x power. And furthermore, we can relate beta squared to the coefficient omega squared LC, where we can get beta equals omega times the square root of L times C. This value is known as the propagation constant. V of x is a phasor, but with a tau exponential to negative j beta x that rotates with the position. It undergoes an angular change with respect to position x. To understand this concept, we can think of it this way. When v of x moves a unit distance on the transmission line, that is, when x is going from 0 to 1, its angle changes by an amount equal to beta. Therefore, beta represents the amount of phase change when the wave is moved by a unit length on the line. Once we find the phasor voltage v of x, it's straightforward to determine its time-domain waveform. We simply connect the tau exponential to j omega t to it and take the real part to get the time-domain voltage wave, which is a times cosine omega t minus beta x plus b times cosine omega t plus beta x. Furthermore, finding v of x is equivalent to finding the current I of x, whose solution is a over z0 times exponential 2 negative j beta x minus b over z0 times exponential 2 j beta x. The time-domain response of the current is a over z0 times cosine omega t minus beta x minus b over z0 times cosine omega t plus beta x. Notably, the coefficient z0 represents the characteristic impedance of the transmission line. This mathematical value describes the relationship between the voltage and current waves on the line, which we will discuss shortly. Okay, an important observation to make here is that we don't explicitly see the electric and magnetic fields in the solutions. Instead, the effects of these fields are included in the circuit through the propagation constant beta and the characteristic impedance Z0. This approach is quite clever. Okay, since the voltage wave V of x varies with position x, we know that it is propagating. Next, we should examine the direction of propagation as well as the wavelength and wave speed.